Assalamu alaikum dear students. Today our sixth lecture of Quantum Mechanics 1. In the previous lecture, lecture 5, we discussed about the linearly dependent and linearly independent vectors. Because if we define dimension and basis of a vector space, firstly we understand the concepts of linearly independent and linearly dependent vectors and differentiate between them. In the previous lecture, we completely described the concepts of linearly independent and dependent vectors and also solved some examples related to the linearly dependent and independent vectors and how to differentiate between them. So, in this lecture, we define and discuss about the dimension and basis of a vector space. This is the second topic of our second unit of quantum mechanics. So also another topic we discuss in this lecture is a Dirac notation, which is also called a Ket-Bra notation. This is the most important and standard notation in quantum mechanics. Mostly we write different state vectors in their notation of Dirac notation, and we solve some examples or exercise numericals using the Dirac notation. So that's why this notation is called the standard notation in quantum mechanics. This is the outline of our lecture. Firstly, we define dimension of a vector space and then basis of a vector space. Dirac notation. Dirac notation is also called the Ket-Bra notation. And what is a Kets? Elements of a vector space. Bra's elements of a dual space. Dual space mean Hilbert space, because in Hilbert space also include linear vector space and some additional properties add, then you can say this is the Hilbert space. We discussed in the previous lecture about Hilbert space. So that's why elements of dual space is called Bra's. Scalar product of Ket-Bra notation or also called a Dirac notation, and related example how to solve these notation with different state vectors, change how to change one state vector to another state vectors, and how to get the inner product or scalar product of two state vectors, or how to get the scalar product of Ket and Bra. These are the examples also in this lecture included. So students activities or practice related the examples of these questions and in the last reference books. Now student, let us start today's topic, dimension and basis of a vector space. So firstly we understand the linearly dependent or independent vectors in the previous lecture. So now we understand dimension and basis of a vector space. So students, linearly independent and dependent vectors are those vectors if all the coefficient of the vectors multiplication is equal to 0, then you can say that these vectors are linearly independent. And if one non-zero vector is present, then it means these are dependent, linearly dependent vectors. So you can revise previous lecture. Now start. What is dimensions of a vector space? The definition of the dimension is the dimension of a vector space is given by the maximum number of linearly independent vectors the space can have. Space can have maximum number of linearly independent vectors. This is called the maximum number of linearly independent vectors are called the dimension of the vector space. For example, if the maximum number of linearly independent vector a space has is n, for example that is phi 1 to phi n, this space is said to be n dimensional because there is the maximum number of linearly independent vector is n. So that's why we can say this space has n-dimensional. In this n-dimensional vector space, any vector psi can be expanded as a linear combination. Psi is equal to summation of I1 to n, A of I, phi of I. Its mean linear combination mean you can take sum of all these vectors and the coefficients. For example, I is equal to 1 to n. So you can write A1 phi 1 plus A2 phi 2 plus A3 phi 3 and so on, an phi of n. For example, if we have three vectors in a space, A1 phi 1, phi 2, phi 3. It means that this space has 3 dimensions. It means the dimension of this space is 3. This is the dimension of a vector space. Because linearly independent vectors are 3, 1, 2 and 3. Now students, the second term of this lecture is basis. In the previous slide, we discussed about dimensions of a vector space. Now, what is the basis of a vector space? The basis of a vector space consists of a set of maximum possible number of linearly independent vectors belonging to that space. Students, this means that if you have any space of n dimensional space, it means n number of vectors are present in that space, or you can also take a 3-dimensional space. It means 3 vectors are present in that space, linearly independent. The maximum possible number means the highest number of the linearly independent vectors of that space which is belonging to that space is called the basis of a vector space. For understanding, we get an example. The set of vectors phi 1, phi 2 to phi n to be denoted in short by phi of I in the brackets. This phi is represents if we can write these vectors in the form of set, then you can write phi of I in the form of set, and I is equal to 1, 2 and 3 and so on n. So, phi of I is called base vectors. It means I represents the basis of a vector space. It is depend on the number of linearly independent vectors. So, similarly, if we have 3 vectors, phi 1, phi 2, phi 3, here I is equal to 1, 2 and 3. So, this is the basis of a vector space, and we can write phi of I which is equal to phi 1, phi 2 and phi 3. So, the basis of this vector space is phi of I, and you can also write in the form of set phi of I in these brackets. So, this is the basis of the vectors, and this set is called the base vectors. Now students, the next term is Dirac notation. This is the standard notation of quantum mechanics, and this notation has given by a scientist Dirac. That's why it is called Dirac notation, or sometimes it is called Ket-Bra notation. In quantum mechanics, Ket-Bra notation is a standard notation for describing quantum states. Students, as we know that any particle represents by a wave function. So, the definition of Dirac notation is the physical state of a system is represented in quantum mechanics by elements of a Hilbert space. These elements is called state vectors. All of you know about what is Hilbert space. We discussed in the previous lecture. And in Hilbert space, which elements belongs to the Hilbert space? These elements are called state vectors. And students, you know that in Hilbert space we use the concepts of vectors. And vectors, set of vector is psi, chi, and phi, and so on. So these elements are called state vectors. Similarly, we said that any particles represents by a wave function. So a particle is also associated with a wave, like this. This is a particle move in this direction and associated with a wave. Its states change according to the time. Means various quantum states. It means it changes its states at different points according to the time. It changes their states. So that state we represent by a wave function which is called psi, and this state is changed by the time. So we write r and t. R is the position of this wave and t is the time. So this is called the wave function. Describing any particle we use wave function. So which having various quantum states. This state wave function having various quantum states. So for defining these states we use standard notation called Dirac notation. This is the second definition of Dirac notation and the understanding of the Dirac notation. We can represent the state vectors in different bases by means of function expansion. It means that if you have a wave function or state vector psi, then you can represent by the basis of the vectors which we defined in the previous slides. And this state of the vectors is represented by a psi, phi, psi I. And if you have the wave function phi, then you can represent in the form of phi, and sometimes you can represents in the form of chi and xi. So it depends on the function expansions which we used for different state functions. So this is also the concepts of Dirac notation is given by a scientist by Dirac, Paul Dirac. Students, we define the Dirac notation. The elements of Dirac notation is Kets and Bras. Firstly, we define Kets and then Bras. What is Kets? Elements of a vector space, also called the elements of a vector space. Dirac denoted the state vector psi by the symbol bar, psi, and angle bracket. And sometime in the mathematics we call the symbol of this symbol is called the greater than. So in the quantum mechanics we call angle bracket, and the whole term is called the ket, and also called the state vector. So we highlight this symbol is called the state vector or ket vector, and simply we say that it is a ket, this symbol. If we have a state vectors in Hilbert space is phi, then you can write phi in the form of Kets. This is the Kets, and Kets belongs to the Hilbert space. or Hilbert vectors, or in short to the Ket space. This is the representation of Kets in quantum mechanics. This representation is most important in quantum mechanics. We used in different problems for solution. So now we define a brass elements of a dual space. What is a dual space? Actually, a Hilbert space is also called a dual space. Dual space means Hilbert space is a set of linear vector space, and but some additional should be added in this space. That's why it calls dual space, and this space is called a complete set, complete space. यानी कि Hilbert space is a complete. So that's why we call dual space. A dual space can be associated with every vector space. So Dirac denoted the elements of a dual space by the symbol angle bracket and bar. In mathematics, this shows that the less than, and this is the bar, or sometime we used for the determinants. So if we write a vector in that space, then we can say that it is called a bra vector, which he called a bra vector or simply a bra. The elements psi represents a bra, and this is also called the state vector. And the position of a state vector which we replace by the Kets. So that's why the name of this state vector is changed. Note, for every Ket there exists a unique bra and vice versa. So if we combine these two terms, then you can say that this is the Dirac notation. And the scalar product or inner product of two vectors. So if we write a state vector, this state vector firstly, the bra vector, and then we write this state vector, but the symbol of bar is common in both. This is called the inner product or scalar product of two vectors. So this is the representation of Dirac notation, and we find in different numericals we find Ket or bra or inner product of two vectors. Now students, here is the complete form of Dirac notation. This is called bra-Ket notation for the scalar product. Dirac denoted the scalar or inner product by the symbol this. We use two angle brackets and one bar for the inner product or scalar product, which he called a bra-Ket vector or a state vector. For instance, the scalar product phi and psi is denoted by the bra-Ket, these two angle brackets, and the first represents the bra vector and the second represents the Ket vector. So we can write phi and psi, the Hilbert space elements, vectors elements, and in the form of state vector or Dirac notation we can write phi and psi in this form. Note, when a Ket is multiplied by a complex number, we also get a Ket or bra. For example, if we write, we can write in mathematics, Ket vector also represents in the form of column, and the bra vector also represents in the form of row. For example, if we have a vector psi, Ket vector psi, we can represent in the form of column. That's like if we have three vectors or n number of vectors, so we can represent in the form of column. It means x1, let's suppose x1, x2 and x3 if we have three elements. So also write bra in the form of column, in the form of row. So psi of bra, but here we use bra for phi, so we can write phi. If we change the ket vector into bra, then we can multiply by a complex number and we can get the complex conjugate of that state vector of ket, then we can get bra vector. But simply we can write phi is a so this is equal to, in the form of rho, a1 a2, or simply we can write x1 x2 and x3. This is the example of writing the ket and bra vectors in the form of rows and columns. But if we change these two state vectors in the other form of state vectors and vice versa, then we can operate some mathematics rule on that vector state vectors, then we can change this. So we can solve an example of these notation, then you can understand what is the bracket vector and how we can change these two vectors in by each other. Now students, here we practice Dirac notation, how to write one state vectors in the form of other state vectors, and ket in the form of bra and bra in the form of ket. So firstly, if we have a ket vector psi, so the ket vector, we know that the ket vector is right in this form. So the ket vector is equal to, we know that we can write ket vector in the form of column 1 and 0. And if the same vector, we can take bra vector, which can be write in the form of row 1 0. But here is a simple question, we can change ket into bra, but the main rule how to change ket into bra, firstly we can taking complex conjugate. In mathematics, for example, if we have a plus iota b, we take complex conjugate. Simply we write for complex conjugate C and M. Complex conjugate. So we take complex conjugate A minus iota B. It means that we change the sign with the complex number, not with the real number. So the real number, simply change the sign of the complex number. Here is a complex number is iota. Here is the complex number is iota. The sign with the iota is plus. So if we take complex conjugate, then you can write minus iota. Similarly, in this vector, state vector, here is no complex number. 1 is also a real number, 0 is also a real number. That's why we can write 1 and 0 in the form of bra. But here we write iota in the replacement of 1. Then you can change the sign and the bra and the row column into. So we can take two operation. One is complex conjugate, change the sign of the complex conjugate, and the other is column changes into the row. So in mathematics, if we have a vector or which is equal to iota and 0, iota and 0. So we take conjugate. Conjugate means only change the sign of the complex number. So here is plus iota, we can write minus iota. It means that we take complex conjugate. So now we taking the transpose. Transpose means changes column into with row, column into row. So we take transpose. Transpose mean that we change column into row, minus iota and 0. So this is equal to asterisk. Asterisk means we change the a vector into asterisk by taking complex conjugate and transpose. So same operation we apply in these state vectors cat and bra. If we change the cat into bra, then firstly we change the sign of this state vector, means we take the complex conjugate. After that we change the row column into row. Then you can write psi of state vector cat, which is equal to the state vector of bra. So this is the operation we use in some numericals for solving these conditions. So if we write these two terms in the form of Dirac notation, then you can write phi, firstly this state vector and secondly this state vector. So this is called the inner product. So we multiply both 1 0, this is the bra vector and this is the cat vector 1 0. So we multiply by these vectors, first row with first column. This is the rule of mathematics for multiplication. So 1 multiplied by 1 plus 0 multiplied by 0. So which is equal to 1. This is the solution. Similarly, students, you can also solve some question. Here we change this state vector into this form of state vector. For practice, we assign some question. For students, you can solve and get answer and the understanding of this Dirac notation. Same order of matrix should be edited, but if the order of the matrix is different, then you cannot edit these two vectors or multiply. This is the rule of mathematics. For example, this is the two terms in this matrix and in this matrix has two terms. So we can multiply these two. Now students, here is two examples for all of you for the practice of the state vectors, how to change the state vector, one state vector into an other state vectors, and the other state vector change into first one state vector. So it's mean the Dirac notation ket vector change into bra vector and bra vector change into ket vector. This is the first state vector, which is called bra vector, which is equal to 0, 4 iota, 2 plus 2 iota. And this is the ket vector, which is equal to 1, 2 plus 3 iota, square root of 2 e raised to power iota pi by 5. So students, you have remembered that only change the sign of the complex number, not a real number. And also for changing the one state vector to the other vectors, you can change row with column and column with row. So that these two state vectors can change with each other, ket vector into bra vector and bra vector into ket vector. So students, you can solve and give reply me the answer of these two questions. Now students, in the previous slide, for the understanding of a scalar product or inner product of two state vectors, we simply multiply two state vectors. Now here is an example for the understanding of quantum mechanics, the product of two state vectors or ket or bra in the form of Dirac notation. The scalar product of ket vector, or it is also called a state vector, and a state vector phi, which is also called a bra vector, which are given. The bra vector is equal to 2 iota 2 plus 3 iota, and the ket vector, or simply a ket, is written as, which is equal to minus 3 iota 2 plus iota over 4. So if we take inner product, simply we multiply these two state vectors, ket and bra. Firstly we write bra and then ket. This is the form of inner product or scalar product. So if these two state vectors are given and question is that find the scalar product. So how we can calculate the scalar product of these two state vectors? Simply we take a product of these two state vectors in this form, which is equal to 2 iota 2 plus 3 iota minus 3 iota 2 plus iota or 4. So simply we multiply by this row by column. So this row is multiplied by this column. So 2 multiplied by minus 3 iota, iota multiplied by 2 plus iota, and 3 iota multiplied by 4. So 2 multiplied by minus 3 iota plus iota, we use the addition sign when we multiply these two matrices in mathematics. Similarly, we use this concept here, plus sign, plus iota, 2 plus iota multiplied by 2 plus iota plus 4 multiplied by 3 iota multiplied by 2 plus 3 iota multiplied by 4. This is the whole term, 2 plus 3 iota, which is multiplied by 4. So 2 multiplied by 3 minus 6, 2 3s are 6, plus minus minus 6 iota, plus 2 iota plus 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 iota into iota, iota square, plus 4 into 2 8, plus 4 multiplied by 3 12 iota. So minus 6 iota plus 2 iota plus 12 iota. So 12 minus 6, 6 iota, 6 iota plus 2 iota, which is equal to 8 iota, plus iota square plus 8 iota square. We know that students in mathematics, iota square, which is equal to -1. So we write in the replacement of iota square -1 plus 8. So 8 minus 1 plus 7, because the bigger terms having the plus sign. So 8 minus 1 plus 7, 8 iota plus 7. This is the example of scalar product of two vectors and how to multiply cat by bra. So this is the example. Similarly, you can solve and other questions. Now students, this is the topic of our today lecture. The short terms we discuss in this lecture: dimension, basis, and the Dirac notation, and some example related to these topics we solved and practice in this class. I hope so you can understand all these terms. If you have any problems, you can ask me on comment box. These are the reference books. Regarding to these details of these books, you can also search in these books. The data is collected from these books. Thank you so much, and Allah Hafiz.